I'm so, I guess, proud that we are all together. Andrew has emphasized how sorry we are that we are not there. Ignore the typo on the title. Mark Nyrink and I met in Colorado, in Boulder, sometime in June or July, and it just so happened that Nicola had emailed Mark on his new article at that the day before, and so due to common work and interests between, I guess at that time was Nicola, Barbara Drossel, Mark, and I. We started having Zoom meetings, which were incredibly interesting. And much later on, due to the generosity of Nicola and Flavio and Mark, who have so well organized this workshop and even enabled us to attend from a distance. So first of all, a big thank you, and how we have all been able to bring together physicists from a very wide variety of topics, which is the point. Recently, Andrew and I and Liz Mullen and Stu Kaufman have proposed a topic of biocosmology. I believe it stems directly, very, you might not see how, but it stems directly on problems that physics has today, starting with quantum theory, and go up from there to classical mechanics, fluid dynamics, and so on and so forth. And so I will describe how a curiosity about biology can inform a development of physics out of some trouble we face ourselves today. Let me thank the large number of people here that I would like to thank. Just give me 1 second. So, of course, to begin with, I don't know if Barbara happens to be watching right now, but Barbara started a lot of my thinking together with when she visited PI with Liz Mullen in 2016. George Ellis, the quantum mechanics crowd of Aronoff, and this two-state vector formalism has also helped me. Discussions here with Greg Iyink, Amir Jafari, and Ethan Vishniak, who are going to speak later today, have been incredibly helpful. Nicolas Gizin, of course, incredibly has a insight and really is at the forefront of thinking in these deep issues of physics. Who else here? Mark, of course, is my go-to person because he can dabble in and out in cosmology very well, and so I deeply rely on him. And this research is also going to be informed by some computer scientists at Microsoft, at Google, and of course, Simon Zwart, who was so influential when he visited Perimeter and discussed with Lee Smolin and I his first views. This was in 2016. On the results that it was getting by on numerical simulations, and that I cannot pronounce your first name, but Buchholz described yesterday very well on time reversibility in numerical simulations. So it's a large crowd of contributors here that I need to thank for how I came to this view today. I was moderating a debate on life a couple of days ago. That's why I missed much of Tim Maudlin's talk. They described my short bio was like this: as a new scientific view that allows us to see life through the lens of black holes and dark matter and dark energy. I guess for the non expert crowd, I usually say that we are trying to compare living systems with non-living systems to the best of our abilities quantitatively. And so this is really what I feel we have done with a proposal, which is not exact, but it's a proposal for a quantitative comparison of a living system and a non-living system. In this case, it's going to be a quantity measured or derived for the cosmos and a quantity derived for a living system, and it's going to be the number of configurations in the phase space. This is a busy slide. I sometimes have it just to say for audiences that don't know me, to say that I have experience. I've worked in all the pipeline in cosmology, from data acquisition to data embedding in fundamental physics. And today I specialize more or less in issues related to the arrow of time. And it was very interesting that during the debate on life at the Institute of Arts and Ideas, who had Sarah Walker, Alex Rosenberg, and John Joe McFadden, and they at some point asked if issues on irreversibility and questions on the arrow of life could bring the answer to how life has begun. And the arrow of time could answer issues about life. And of course, I didn't go into that, but it was an interesting perspective.
Marina.
Yeah.
I just want to confirm, are we still on the opening slide, or did you already click on?
Oh my God, no, I've clicked through.
Oh, because we're still seeing the first slide.
Okay, right. Gosh, I am in on the seventh slide. Okay, let's not worry. That's this is an ongoing. It's a feedback between the system and its environment, so we can adapt to problems. How about these? Do you see if I have it like this?
Now we see the slides updating. Yes.
So you guys didn't see this thank you?
Okay, but we heard it. Yeah, we heard it. Okay.
Oh, goodness me. Okay, at least, I mean, yeah, I need to thank you guys. Please read your names, otherwise I'm gonna come out as a really rude person. Okay, so I was just saying this is the data to theory pipeline that I was. Give me 1 second to grab a glass of water. I usually use this slide when for audiences that are not familiar with my work, just to say that the knowledge that I've come to develop in biocosmology comes from very broad experience in cosmology, and also the topic that we're doing today with this meeting of bringing together physicists from very many areas in physics that traditionally are disconnected. And we discussed this in our Zoom meetings, that there is traditionally not a lot of overlap in communication of our results, which I think it's so special about the meeting that Nicola is with Flavio Mark are organizing, makes it possible. Okay, so this I already said that. And I believe that the goal of biocosmology is to enable progress in theoretical physics. Essentially, I'm going to, by looking at living systems, I want to understand the problems that we are facing in theoretical physics. And this is completely non-intuitive. So I hope I will be able to explain a little bit how that can come. As Tim Maudlin said so well in his talk, the part that I could see is the first thing when you start to address questions of describing a system, whether or not is deterministic or not deterministic, you need to describe a state, and what is state, and to describe a state, you need a choice of ontology. And so that's how we're going to start, and by finding that the easier footing between biology and cosmology is a comparison of the number of microstates at the classical level, if you'd like. So I think that Andrew described an inventory of microstates of the universe today. That we had, let me see if I had the radiation, I don't have, but the inventory has been evolving. We had first the entropy associated with the cosmic microwave background, which is around 10 to the 80. Roger Penrose then proposed this number 10 to the 100, associated with the entropy if black holes, massive black holes, were at the center of every galaxy. And of course, most recently, we have dark energy with Sol here winning the Nobel Prize for it. But so the dark energy dominating the entropy budget of the universe means that the likelihood of the initial conditions to the Big Bang is 1 in this number here, e to the 10 to the 124. And so what happens here is that this is where I come in. The counting of our understanding of the universe in cosmology is barren, or does not include anything that could be said to be a living system. I'm not going to go into the definition of what a living system is. This is actually a very funny detail. On Monday, somebody said, just like in quantum mechanics, we say, or it was famously said, and I don't remember by whom, that someone who claims to understand quantum mechanics really does not understand quantum mechanics. It was proposed that somebody who claims to understand life equally, just like in quantum mechanics, really does not understand what life is, and so that life also resists definitions. So in this case, usually we don't count living systems in the inventory of entropy to the universe, because of course the planet is tiny. This number of microstates cannot be comparable to the number of microstates in the entire universe, much less if the universe is dominated by the energy of the vacuum. And we don't know how to count life from a rigorous theoretical physics perspective. And in a reductionism view, the number of particles contained in the biosphere is very small, and does not compare at all with the number of particles in the universe. And so from all these points of view, the contribution of life to the budget of microstates in the universe is negligible. And so here I need to just say, why is it that I'm talking about biology? My job, what I do, what I find myself, the best description of my activity is I search for a description of reality. And what this might be called, I don't matter, so I don't mind so much. I will call it for now that I'm a theoretical physicist, and so I'm trying to find a theoretical physics description. But throughout the talk, when I say theoretical physics, I don't mean just what we have today in theoretical physics, but what I want theoretical physics to grow and to become and to be able to describe as it evolves in say centuries to come. Particularly, I don't have an interest in biology other than how it can help me understand puzzles like we are discussing in this meeting of determinism, or the randomness of the ontology, if random numbers are ontologically random, for example. So that's my interest in biology and how it can help me do that. What is a description of reality? In this sense, I mean, like Roger's quest for understanding reality, I don't mean anything mythical or magical, as many times when you talk about emergent or top-down phenomena, those words get associated. I just mean in the sense that you're going to describe reality to the best of your abilities. And a lot of us in the school of thought that I kind of come from, we don't really mind which fields you have to cross in order to understand the world around you. You just go and cross the boundaries, and sometimes you find yourself in biology. But if it helps describe, if it helps you to understand what you observe in the world, then so be it. What is the difficulty of understanding biology in a physics point of view? Of course, we have the Lagrangian, the standard model, and I don't think any of us here are in the field that we would dispute the standard model Lagrangian. But I should say that the standard model of particle physics is very disputed. Biology, we don't have a Lagrangian. Most importantly, if you don't take anything else from my talk, is this part. We don't know the elementary degrees of freedom of biology. And the assumption here is that the degrees of freedom in particle physics are not the degrees of freedom in biology. By which I mean, again, we don't know the elementary particles in biology. What would be the elementary particles? Because we don't know what is the ontology in biology. And this is something which is very key and novel, and it's the part that might come to help physics. This is actually a little bit too fast, so let me see. Okay, so I'll go here. What we have proposed, or what Stu Kaufman has proposed to understand how living systems evolve, is a technique used to describe sometimes sociology or economy, called combinatorial innovation, which means that at each step, two elements of the system combine, and they form themselves, in that combination, a new degree of freedom, a genuine new degree of freedom, not an effective degree of freedom, as it could be the case of the standard model when you have an effective regime. And this equation here, which is going to drive the results and the counting of the large numbers of microstates, is developed by Stu. I will describe it a little bit better later on, but the idea that is at hand here, which I think is novel in theoretical physics, is that a new elementary particle formed by the combination of two elements, and this is genuinely new elementary particle, might pop up in our language in living systems by combinatorial innovation. And we have 3 papers out. I just have 2 abstracts here. The third one is the mathematics of this equation, the tap equation, which involves towers of exponentials and the mathematical operation called tetration. for just funny interest, I did the press release of this science. I happened to be on Everest Base Camp attempting to climb Everest, just not by design, but because it had to be like that. And the press release is live at this site, biocosmology.earth. Just with this. And if you want to watch a different press release, that will be one. There was an article released also by the Institute of Arts and Ideas by myself and Ed McGovern. And the funny thing is that 24 hours before I had to do this press release from Everest Base Camp without internet or electricity or water, I had to do an acclimatization peak for my Everest summit. This is the article that came out. And so now let's go into the physics of what is new that we're proposing might be at play in biological systems. By comparing, I'm going to explain what is new in biological systems by comparing it to a very famous example that we know in particle physics and in cosmology, which is the evolution of the universe in this very first few minutes, when it starts with a very, after inflation, say, the universe cools down, and for the first time, two nucleons combine to form a bound state, which is the proton-neutron. For the first time, this is a stable bound state, deuterium. So in the standard model of particle physics, deuterium is an effective degree of freedom, and it is not occurring before age 2 minutes of the universe because high energy photons destabilize the nucleons and the bound state is unstable. The elements that are heavier than lithium are created later by supernovas. That's besides the point. Here we can compare physics and biology through this. In physics, deuterium could have been derived before it appeared at 2 minutes, age 2 minutes. If you have the Lagrangian, the standard model, arguably you could write down that and derive that an effective degree of freedom called deuterium would appear as the energy goes down. You have the Lagrangian, you solve the equations of motion with a lot of expensive mathematics, but you would be able to derive it. And in this case, what happens in a bound state, as in living systems, when a new bound state of two elements in living systems occurs, that is not predictable. And in this sense, it's as if in physics, a new quark particle or a top quark would have popped up all the time. And so if you have a system in which genuinely new degrees of freedom are emergent spontaneously at all times, describing that system by a Lagrangian is going to be very difficult. And I will explain why those are novel. So, like I said, the deuterium is an effective degree of freedom. And in theoretical physics, we have this assumption that there is causal closure at the microscopical level. And ergodicity, the evolution is Liouville. You can call it Liouville classically or quantum mechanically, with all the problems that entails. I'm not going to speak about unitarity or the violations of unitarity or not, but we assume that the system will revisit the same state after a passing of a Poincaré time. This is standard classical mechanics or Hilbert space. So as a physicist, I grew up believing that the description of the standard model would describe everything we have today, that we could be integrating a large number of equations of motion 10 to the 25, be it Newtonian or Schrodinger's equation, to predict the next step of evolution of the many-body system. And then we can also integrate, limited only by practical purposes, the same number of equations to predict what a person is going to decide. And you'll be surprised that this view is held by a large number of theoretical physicists that I speak with all the time. And so,
Marina, this is the 10-minute mark plus 5 minutes questions afterwards, just to note.
Okay, good. So does that equation, does that description of the world, is it true in principle or in practice? And sorry, let me just go. During interaction with computer scientists at Google, at Google and Microsoft, they have led me to believe that themselves, I know this comes as very surprising, the description of a living system at a computational level is never going to be attainable. This is science that I cannot, unfortunately, not cite because it's screened behind Google security. But this is the impression I have. And also, as a physicist, I started to question that what happens in life, is it really from a practical or a principle point of view? Is it possible to describe it by reductionist techniques of integration of a large number of equations of motion? So the possibility here is that there is a large number of similarities between a living system and a quantum system. A living system defines separation between object and context, just like a quantum system does. And so the techniques we developed in biocosmology to try to think differently, to describe a system that cannot be studied by traditional physics technology, might be the right type of thinking that we need in theoretical physics. In my opinion, the problems in contemporary physics are caused by, we have, and I know this is a little bit shocking, we don't have an operational definition of complexity, of information, and of entropy. We can define these for particular purposes, but at a fundamental level, this is really difficult to obtain, and this is true in biology. So just before I describe how we obtained very large numbers for the number of microstates of the biosphere, these are the inputs that came from into biocosmology, so computer science. And here, Simon Zwart, I think, was the first person that alerted me for the problems of numerically simulating the continuum, the fundamental structure of time, a lot of data analyses, and complex systems in biology, certainly. So what I've explained all of these, and the equation that we have here, in which this is a very simple equation, that we have some variables here, just to parameters here to better describe the evolution of a living system. We're going to suppose that it's the evolution of life on Earth. And this is a little bit wrong. Yes, so we use this equation to describe evolution of life on Earth and try to count the number of configuration, number of microstates. We choose an ontology, which is for simplicity called CHENOPS, which is the number of elements present in life. We start the simulation at 3.7 billion years ago. The extinction rate, which is by combinations in this combinatorial innovation method that do not survive for some purpose, and we choose an A, which alpha, which is just the difficulty of elements defining itself. And what happens, which is very typical of this equation, is an explosion at some point. This is a characteristic hockey stick behavior of the number of microstates. So on the y-axis, this is the number of microstates, and the x-axis, it's the number of time steps. Being 0 here is at the onset of life on Earth, and we stopped just because of computational overload at the time of the first RNA molecule. But it really is characteristic of what biology sees to say, for example, the number of species or the number of any measure of complexity on the planet. There is a hockey stick behavior. There's a long plateau, and after some time, this equation typically explodes and generates, by this combinatorial innovation method, a large number of possibilities. And the outer plot is just the same as the inner plot, and the unique difference is that the very last point here is the next point after this one. And so this one is 10 to the 5, and the next point is already 10 to the 206. Just because of this tetration evolution. Now, this is, let me just go here more or less. It's a proposal for what biology might be doing. And we get numbers in microstates of the biosphere by this assumption that life, the new compounds in the living system are genuinely new. We get numbers which are quite very large. So in the cosmos, the entropy of the cosmic horizon is 10 to the 124, like Andrew said, and life, it's traditional standard physics is like this. And we've got towers of exponentials given by this combinatorial innovation method, which are very dependent on the parameters you put in the equation, but give an indication of the power that can be contained in a system that genuinely creates novel degrees of freedom. And I'm going to go to my summary, and then I will, if we have time, I will explain, because I forgot why is the degrees of freedom emerged in biology? Why are they novel? But so we are trying to study living systems from first principles. This is the summary. We're not doing biophysics and not astrobiology. We just genuinely try to learn from looking at the evolution of a living system. What can we learn from physics, because a living system, the problems that it proposes are quite similar in some aspects with the problems that we face in fundamental physics. Now, the problems we face have already been addressed in physics by condensed matter laureates, the solid state, so emergent phenomena that are not reductionist or reducible to simpler explanations. Maybe this afternoon, Greg Eyink and Ethan Vishniak will describe something similar that might be happening in fluid mechanics, which they described to us as anomalous dissipation. Barbara explained really well to me what are and Amir Jafari as well, what are the problems with the proofs of the fluctuation dissipation theorem. Again, this is connected also. Nicola described so well why we have the real numbers that might not be real, and Mark described what is the information present in the initial state enough to describe what we have today. And I forgot to end this sentence here, which is the pen and paper world might not exist, which for me is the what I call it, the pen and paper world, to be our description of classical mechanics in the form of theorems that we are having trouble by the work of Simon Svart and his collaborators, and by the work of Greg Eying and Ethan Vishniak, to reproduce either numerically or even in real world experiments. Am I 10 minutes?
You have 1 more minute, and then we have 5 minutes time for questions.
Oh, okay. So I completely forgot this very famous model of Stew as to why a bound state that occurs in a living system is novel, in the sense that the deuterium, when the universe was 2 minutes old, is not, because the new degree of freedom of deuterium is effective, and in biology the claim is that it is not effective degree of freedom, it's a novel degree of freedom. So he describes it like this: imagine that you have a fish swimming in a lake. A fish as a swimming bladder. There happens to swim a bacteria by that enters the swimming bladder of this fish for reasons that one cannot anticipate easily. And so the bacterium enters the swimming bladder of the fish and happens to find that environment quite hospitable and conducive to selectively positive, in the sense of I have a longer life if I stay in the swimming bladder of the fish, and the fish might have an advantage from the bacterium as well. Now, what happens in biology is this new bound state of the swimming bladder of the fish and the bacterium are now evolving together, and this evolution of the new bound state is not easily derivable a priori from some theory or evolution rule for a living system from a physical sense, from a theoretical physics perspective. It's not possible to derive why would the bacteria happen to swim by and happen to find the conditions of the swimming bladder hospitable. This is an example for what characterizes what we might call in physics. We have no other way than it's a random chance that the bacterium happened to find the swimming bladder hospitable and a good way to where to live. And so for all purposes in our language, we would call this a complete independent and novel elementary degree of freedom. It's the assumption. It's not, of course, we don't know. This is Stu, Lee, Andrew, and I. We by no means assume or are stating that it's definitely the case. But as we've been studying living systems and what could be the best physical description of living systems for the last 4 years, and to the best of our abilities, describing the bound systems as genuinely new elementary degrees of freedom is the best way that we can describe them. And so it's a first attempt to take seriously and learn from living systems from the point of view of physics. And in this sense, we were able to compare the number of microstates that can be generated in the biosphere to the number of microstates, classical microstates, in the configuration space of the universe. And criticism, I'm all open to criticism, and really looking forward for the afternoon talks of today.
All right, thank you very much.
All right. So we take 15 minutes break and we start. Huh? No. Just one. Okay.
I don't understand. I don't see. Oh, okay.
Someone else. We have an hour late, but it's like 30 seconds question.
Okay, we have time for a very brief question with a brief answer. Did you say?
No, I don't.
Oh.
No. It's not the other one.
Oh. Okay, there are no questions, but Marina will be online.
Oh, then I could say not something related to this, but also related to the meeting, that I would have nagged you already all if I was there. Which is so as a result of this meeting and our Zoom discussions, there is a Frontiers in Physics issue that I am going to edit, and we can or not contribute with your talks or any work that you have related to the meeting that you are organizing. If you are interested, it's really a very nice compilation of topics that compose the seminars of this meeting. So maybe later on, I will be sending invitations. If we all agree later in another discussion by Zoom or something, there's a Frontiers in Physics. What topic is it? I guess it's going to be several topics within physics, but complex physics or quantum mechanics and all of the issues described and discussed by all of you. And now go to the. Yeah, it looks like it's a lovely sunny day. You have better things to do with your time.
Thank you very much, Marina.
Thank you.